So based upon that, we can come up with a suitable compatibility condition that we need to have zero displacement at any one end of the bar with respect to the other. So basically, I mean, the ends are fixed, so the ends relative to one another can't move. You can have some movement in between. You will have some movement in between, because if you break this bar up into the two sections, essentially, and break it up right here, you're going to get one section on top here that is under tension. So the magnitude of the force there is going to be equal to FA or AY, or whichever kind of naming system you want to be using. And then you're going to get this section at the bottom here that's under compression, and that compression is going to be equal to FB. So essentially, this section is going to get longer, this section is going to get smaller, and the point in the middle where the force is applied is going to move downward a little bit. And essentially, every kind of part in between is going to shift downwards a little bit. It's going to be zero at the ends and zero at this end, and then largest in the middle. So we can if we know that the total displacement needs to be equal to zero, we can find out what the total displacement is by adding up the displacements of the individual components in terms of P, L, in terms of their P's, their L's, in terms of their loads, in terms of their lengths, in terms of their cross-sectional areas, and in terms of the Young's modulus for those both. So just taking those values, we got the FA, the tensile load on top, times the length from A to C, from the top to where the force is applied. Got the cross-sectional area here, and we've got our E. And then we've got on the other side, we've got the FB, not on the other side, and then minus the FB times the LCB, so the length from here to here, and then divided by its cross-sectional area and its E. Now, of course, in this instance, we could eliminate the effect of E and A just by multiplying by E and A, and then, gets multiplied out, goes to the zero, disappears into the void. Then we don't have to worry about it. So then we're just left with a term for FA can be solved for in terms of FB LCB divided by LAC. And then we can further kind of reduce that down to figure out what FA is in terms of P, just by keeping in mind our relationship that FA plus FB needs to be equal to P, and that LAC plus LCB needs to be equal to L. So based upon those relationships, we're able to solve for FA and FB in terms of P, L, and the kind of the lengths between the other sides. So that allows us to determine the reactions at the supports in a manner that we wouldn't otherwise have been able to do so just based upon our static equilibrium. So we'll do a quick example here. So we got this rod, and it is mounted between these two walls, and it's got a little collar here, and it's got this little gap here at the end. So we'll copy and paste that over. Okay, so essentially here we've got the So yeah, we got the wall on one side, we've got the gap in the wall on the other side, and then we got the rod with the collar in the middle. So when we load this up, this part's going to stretch. There's going to be initially no load on here until we hit the wall, and then as we continue to load it up, essentially the wall is going to start pushing back. So what's going to happen is we need to kind of first figure out whether or not it's going to hit the wall. So essentially the easiest way to do that would just be to we can just plug our our formula for our deflection into here. So our load will be 20 kilonewtons times the length. So the length, before it hits the wall, the only part that has any stress in it is that 400 millimeters. So 400 millimeters divided by, so it's a rod with a diameter of 10 millimeters, which means a 5 millimeter radius. So the area there is going to be pi times 5 millimeters squared. And then it's a steel rod, so the Young's modulus of steel is 200 GPa, gigapascals. Alright, so a kilonewton per millimeter squared is 1,000 meganewtons per millimeter squared, which is 1,000 megapascal. So kilonewton per millimeter squared cancels out our GPa, or gigapascal, which means that the end result of this will be in millimeters. So 20 times 400 divided by 3.1415 times 5 squared times 200. So that ends up being 0.509 millimeters. So we did verify that this thing is going to want to stretch more than the gap can accommodate. So essentially, that means is that when we hit the wall, we're going to get a situation like this. We are going to get a reaction Bx, and we are going to get a reaction Ax, and we got the color here, and we got our 20 kilonewton force. So there's our free body diagram. So if we want to figure out what Ax and Bx are, and then use that to determine also, and we can use that to determine also if we want kind of how much these things moving overall, then we're going to have to use the same formula that we worked with before. So essentially, the displacement from A to B is equal to the sum of the displacement in the individual sections, and that the previous kind of what we had gone over, it was limited to 0. Here we're not limited to 0, but we're limited to 0.2 millimeters. So that needs to be equal to 0.2 millimeters. So essentially, again, just break it up into the two sections. So we're going to have a bar section here that is a tensile. It's got AX and AX on either side. And then we've got a bar section here that's going to be under compression. bx and bx on either side. And then, so we just doing the sum of the forces in the x direction equals 0. So again, we got minus ax plus 20 kilonewtons minus bx. So that just means that is equal to 0. So moving the stuff over to the other side, got 20 kilonewtons is equal to ax plus bx. So we can figure out the individual components here. So the sum of the i's, that's going to be ax times, this was a 400 millimeter section, the other one's 800 millimeter section. 400 millimeters divided by pi times 5 millimeters squared times 200 GPa plus bx, minus bx minus bx because we drew bx in a compressive state. If we had drawn bx as if it was tensile, then it would be then we'd add it together. But we already assumed bx was going to be in this orientation, so we need to subtract it. So minus bx times 800 millimeters. A and E, that's equal to 0. I'm just going to cancel these two out by multiplying by A and E, because those are the same for both. End up getting AX times 400 millimeters minus BX times 800 millimeters is equal to 0. And AX is equal to BX times 2. Once you can't, BX times 800 millimeters divided by 400 millimeters. So the magnitude of AX needs to be twice that of BX. And then knowing that AX plus BX is equal to 20 kilonewtons, then that is simple enough to solve for there. So if AX plus BX, why am I just redrawing the same equation? So if AX and BX is equal to 20 kilonewtons, and we just plug in the 2BX plus BX is equal to 20 kilonewtons, then 20 kilonewtons divided by 3 gives us a BX of 6.66 kilonewtons. The reaction of the beast. And then 20 minus that gives us our AX. That'll be 13.333, etc., kilonewtons. So if we just want to redraw our free body diagram real quick, just to make, 20 kilonewtons, 15.3 kilonewtons, and 6.66 kilonewtons going that way. So that's about that. That'll allow us to figure out the reactions. which was what was asked. If we wanted to, we could also figure out how much this thing moved when this load was applied, and we could do that just by the easiest way to do that would just be figure out individually what the stretch in the section from A to C was. So just should essentially be this formula here, except we're plugging in instead of 20 kilonewtons, we're plugging in 13.3. I'm going to go ahead and do that because why not? 13.3 times 400 divided by 3.1415 times 5 squared times 200 GPa. So that would give us this thing moving 0.33945 millimeters. So that's less, obviously, less than we saw initially, which shouldn't be surprising because it's being resisted a bit by the reaction at B.